22 School of Chemical Sciences. And then lastly, to round out the series with a talk of Introduction to Spherical Astronomy by Gayatri, my friend from School of Physical Sciences, batch 22. So then when we are inducting the new juniors into the club, we have this tradition of having an induction quiz. And we induct you into the club based on your performance in the quiz. Questions for the quiz will come from these talks and the talks that are coming up in the following week. We have regular talks every Saturday in underscore at 7 p.m. So make sure to attend the talks, make sure to be attentive, and yeah, enjoy. Thanks for the introduction. So, yeah, I'll be talking about how we go about to search for what. I hope you have all read my abstract. If not, find out anyways. What I mean. Content of my talk. First, I'm talking about formation of water in the interstellar media, the reactions, basically formation of the water molecule. Then we look at ortho and para states of water and why they are to us in this discussion. Then we go on to the question: does water exist? So the question: does water exist out there in the universe? We'll be looking into the answer to that. I kind of spoiled it already in the next topic, which is water in solar system. So these are the four topics that I'll be covering today. So formation of water in the interstellar media. First, there's the formation of atomic hydrogen. We'll look at that. Basically, an electron is attracted to a proton and we get an atomic hydrogen. Then formation of atomic oxygen. That is a little more complicated, and for that, these are the processes involved. We know that the lightest atoms are the most easiest to form because they require the least amount. Star burns hydrogen as its fuel, and it converts it into helium. As most of the core's hydrogen is burned into helium, then the nucleosynthesis in the core of the star continues, and we get elements like nitrogen and oxygen. So if the temperature of the core keeps increasing, we get elements until iron. Only the most massive stars, even heavy elements that form the periodic table, which they eject out into the universe when they reach supernova. So these are four reactions that you can see. There are many suggested mechanisms, but these four are the most widely accepted as to the formation of the water molecule. We can go through this. Uh, it involves cosmic rays and it all takes place in the interstellar medium. Another process that is involved in this is the dust frame chemistry, where water forms directly as ice. It does not form as like liquid or vapor. Here I've shown a diagram which shows formation of the H2 molecule. H2 because I couldn't find a good diagram. But this is satisfactory. You can see two H atoms on the surface of a dust grain. They combine, form H2, and the grain absorbs the energy that it needs. Similarly, there can be two H atoms and one oxygen atom that combine together and form ice directly on the surface. All of this is taking place in the molecular clouds where the temperature does not exceed 100 Kelvin. So yeah, obviously ice. Ortho and para states of water. Many of you are probably aware that electrons can exhibit a positive and a negative spin, right? Similarly, the nucleus of an atom also has a characteristic spin. In case of hydrogen molecule, there are two such states, the orthohydrogen state and the parahydrogen state. In case of orthohydrogen, both the spins are in the same direction. Parahydrogen, opposite direction. Similarly, in case of H2O molecule, there are two H, right? So same direction, also opposite direction, parallel. That's it. Now, why is this important to us? Basically, this helps okay. So at lower temperatures, parahydrogen is more stable. And as the temperature increases, that is at room temperature, you get a ratio of ortho and para as 3 is to 1. So, by looking at at the ratio between ortho and para states, you can predict the temperature of the water that you are observing. And this has proven to be quite, this is a method that we use quite often and is very good. So, the third one. Does water exist out there in the universe? The obvious answer? Yes. Does liquid water exist? Probably. As of yet, we have not been able to detect liquid water anywhere. The search for it continues, and as our tech advances, we will probably find liquid water in the future. We do not know. So, what are the methods that we use to detect water? Okay. For one, we use spectroscopy. Spectroscopic analysis of heavenly bodies that helps us detect presence of water in whatever states it is present, solid, liquid, or gas. That is between. And it also helps us determine the temperature at which the water might have formed. So this is the process. We look for water vapor in the infrared, millimeter, and radio wavelengths. Since in these range, the spectroscopic lines are most intense and easier to observe. The problems to this method. Water vapor is present in Earth's atmosphere in quantities varying with time, temperature, season, day and night. It is varying all the time. Therefore, it interferes immensely with the reading that we receive on Earth. Solution. We launch Earth orbiting infrared observatories that are like satellites that are orbiting Earth so that they are free from this interference of the Earth's atmosphere. A prime example of this is the European Infrared Space Observatory. It was launched in the year 1995 and was operational till 1998. This is what it is. And most of the spectroscopic data that we have as of yet is one of the most sensitive spectroscopes ever made. Search for ice. Now, water vapor is sparse. It is a gas. So basically, whatever spectroscopic signature it emits, it is very dim. Therefore, it is very difficult to catch that signature. On the other hand, ice is dense. Therefore, a little bit easier to observe. Much easier to observe, actually. So, these are the two methods that we use to detect ice: spectroscopy and direct in situ analysis. I mentioned a few spectroscopes there, like you can see Mariah 9, YK, Mars Global Survey. These are all probe sent to Mars. Venera and Pioneer Venus, these were also probe. These were probe Venus. Direct in situ analysis is where we directly analyze planets or like whatever sample we want that place atmosphere, and we study the nature of its constituents. This plot that you see is showing the spectroscopic signatures of vapor, ice, and liquid water. You can see that all are different. Studying these signatures, you can predict the lines that you're observing, whether they're ice, water, or in vapor form. Does anyone know what exactly I mean by spectroscopic fingerprints? Or do you have any doubts? Does anyone know? Can anyone answer this? Anyone? Someone from the nearby? Anyone? Just raise your hand and answer if you know. Okay, so yeah. Guess what it might be if you know anything. Signature graph which we get by certain information. Yeah, maybe in the right direction. Like, can you expand on it? Extend your idea? Or someone add on to whatever. Okay, no problem. I'll give you an example. Like the sun is emitting light in all wavelengths, right? So we receive the spectrum. You know it. There's a spectrum. Spectrum, the entire spectrum, electromagnetic spectrum that the sun emits. There are many elements on the surface of sun, and these elements they will absorb like every element will absorb a certain uh, frequency of that light. Therefore, when you study that spectrum, you will detect black lines. That is your emission spectrum, absorption spectrum. Absorption spectrum. So these lines are characteristic to every particular compound. Like water will have a certain spectrum. And in fact, all three states of water, they will have characteristic lines. If you have a device sensitive enough, you can detect. I hope that is clear. Moving on. Water in the solar system. Let's talk about the Mars. A lot of minerals have been found on Martian surface that are hydrated. Like, I'm just taking an example of hydrated salt, like CuSO4 5H2. It is a hydrated salt. Similarly, many minerals have been found that contains water of crystalline. And there is water ice beneath the poles. There are many valleys and channels observed on the Martian surface, which suggest that water, liquid water, may have flown on Mars sometime in the past. It is also possible that some primitive ocean might have existed on planet Mars long time back. Now, why do we think Mars's internal energy, responsible for hydrothermal activity, may have been able to maintain the circulation of liquid water on the surface for a certain time? Mars is less dense than Earth. This leads to there being a lesser escape velocity. Therefore, things escape from Martian atmosphere. This is the reason that people believe that water might have existed. Thus, liquid water is currently we haven't found liquid water on Mars. Okay, so like when there was water, that was the period when valleys and such channels. Yes. Moving on to Europe. It is one of Jupiter's moons. In fact, there are four Galilean moons. I believe you might be aware of that. Can anyone name the four Galilean moons? Sorry, do you repeat? Europa. Okay. Io. Okay. Ganymede. Anyone else? Okay, I heard you both. I'm just messing with you. Okay, so this is Europa. Earth has tectonic plates covering the surface. And these tectonic plates are moving molten lava. We know this, right? We have studied Earth. So the study of Europa reveals that there are icy plates on Europa's surface that are probably moving on some liquid medium. Scientists are almost certain that this medium actually a saltwater ocean that is in fact twice as large as all of Earth's water body combined. NASA is sending its Europa Clipper spacecraft in 2024 studying whether Europa has the port line, and it is scheduled to enter the orbit and begin its mission in 2030. A reason why scientists believe the tidal effects due to Jupiter on Europa and other satellites of Jupiter on Europa again is probably strong enough to prevent total condensation of water underneath the icy surface. To make it simpler, what I've tried to depict in the PowerPoint, here is an image. This image shows that there's a frozen lake, which has like the top layer of the lake is frozen, but underneath there is light. The water is not completely frozen. This is due to the anomalous expansion of water. Everyone knows that, right? Okay. Right. This is due to anomalous expansion of water and These tidal effects may have prevented total freezing of the water covering the entire surface of Europe. Therefore, scientists are very curious as to whether or not life is on Europe. It makes sense, right? You look for life where there's water. Moving on. Titan, one of Saturn's moons. Titan has nitrogen in its atmosphere. Its surface pressure is 1.5 atm. What's the surface pressure of Earth? Something like 1. Any more values? Okay, mistake. So surface pressure is 1.5, close to that of Earth. More, but not by a long shot. Third, complex organic molecules, hydrocarbons, and nitrites have been detected on Titan. Now, these are the compounds that are precursors to amino acids. Therefore, scientists are very curious that there might be life. The European probe hydrates, what did it do? It went there to look for water. Because first thing to do, whether or not there is life, to look for water. If there's water, well, the probability just shoots up. So that's what it did. This probe, it detected many pebbles on Titan's surface, which on infrared analysis revealed that they were actually ice. So yeah, we are very curious about whether or not Titan actually has life or might sustain life. Well, that's it. With this, I come to the end of my presentation. I hope you all learned a lot. I didn't have questions. No questions? No? I guess I didn't have it. Thank you. Moving on to my friend, Vishal Meena.
Speak louder. Vishal, speak louder. From the school of campus. Don't hesitate to ask questions. You can like stop me middle of the talk if the question is like smaller than a sentence to answer. So let's go. First thing we'll be talking about a quick view on astrophotography. Astrophotography, like if we want to do science, for example, Asmi was talking about detecting water on celestial objects. So to do that, we first need to capture the data, probably using a imaging sensor to image that light so that we can capture the light and study it later. So photography is actually very necessary to do astronomical sciences. Here are the pictures of the moon and Orion nebula. That is the oldest surviving image of the moon from 1860, and this is the picture given. Uh, Photography depends on various variables. For example, your the image you are like the object you're imaging, your sensor, the exposure time of your sensor, and many. So here is the example of what happens when you increase the exposure time. That image was taken with a very little exposure time, and this one was taken with a relatively large exposure time. So there is an increase in detail, a lot of increase in detail. So you can fine tune this variable to get a better picture. The better picture will turn into a better data for spectroscopy and other things. Moving ahead, let's talk about the sensors that we will use to get the image, namely the imaging sensors. For example, there is a sensor, or probably a webcam, which has been zoomed in using a microscope. Short summary on sensors. Now I would like to ask a question. Like, what do you think when we talk about capturing the photons to form an image? Like the basic idea, not the circuit diagrams and all, just the basic idea. Like we are trying to capture photons that are coming from a celestial object and like storing the data. Any ideas? We need to capture photons. That's it. Yeah. Semiconductors are the things that we use, but like basic principle, like basic idea that we can use to collect photons, and then what we can do. Not the circuit diagrams or the physics behind it. Just like a basic idea that you will get in your mind when someone says imaging. How do we image things? Anyone? Bolo? No? So let's use an analogy to explain that. Let us assume that it's raining photons. Actually, it rains photons all the time. So we will collect those photons in a bucket. The bucket will have certain depth, certain size, certain amount of photos that can fit into that bucket. That this bucket can do only one thing. The photons that fall into this bucket, the bucket measures its intensity, like the number of photons that fall into this bucket. So there are about 10 photons in this bucket. Now we take a lot of these buckets and combine them in a grid-like pattern, where we will take output of each of these sensors to say and convert them into an image. And here we are talking about a color sensor. A color sensor is basically those buckets but arranged in a grid-like pattern with color filters on top, so that only the light of a specific color or specific wavelength will enter those sensors, and those pixels, not sensors. Pixels will only measure the intensity of that particular wavelength. Now, there are red, green, and blue. The colors that we can use, like combine these colors, and we can create almost all the colors that we can see. So no one would like to question why there are two green pixels and only one red and one blue. Or do you know the answer? पता है किसी को क्यों green है पर तो पूछो भाई. Green is in the middle of the color. Yeah, so our eye is like most sensitive to that color, so we have like capture more green data so that we can produce a better color image, better color accurate image. So for example, if the red sensor is reading like full, like let us have a scale 0.5 and 1. If red is reading 1, green is reading half, or blue is reading half, the colors will get like extrapolated and it will produce probably a yellow color after combining like RGB values. We combine them in ratios, we will get different colors. Now, we actually didn't use a color sensor to photograph the moon. We used the monochrome sensor. And the monochrome sensor is just those buckets without that filter. That's a monochrome sensor. It is just it has a band of wavelength that it will accept that the semiconductor is sensitive to and record the intensity of all the photons regardless of wavelength, the intensity of photon that is falling, basically that's it, without a color filter. And we read out those values, and as we have a grid-like pattern, it's like a Cartesian plane. We can locate this one, this one. So we get the data out of them, project them to a screen with the LED bulbs. You can say like pixels are such LED bulbs, and light them up accordingly to the intensity of photon each and every one of these buckets received, and we can replicate the things that the sensor saw. That is just the basic principle behind imaging. Now, moving on to the image of the moon we took. This is the image. Actually, it is compressed, but this is the image. Now, what we did to get this image? We used some equipment, obviously. Every experiment uses equipment. So, first equipment, gloves very own 8-inch telescope. 8-inch here refers to the diameter of the mirror, like aperture of the telescope. And the sensor, this is the Skyres 236M, a monochrome sensor. That's it, nothing fancy about it. It's a planetary sensor, like used to capture planetary images. Like if you want to capture the image of Jupiter, you will use this sensor. But it's monochrome. And a processing unit. This one specifically, and bit of manpower from our seniors, me and my batchmate. Then actually, when we were like capturing the data for this image, it was a event. The event was going on, a lunar event to be precise. Super blue moon. Blue moon is just like two full moons in a month, and super moon because the moon was like closer to Earth at that time. So it was the perfect time to image the moon because there is like it is more bright and closer, so you can get better details in the image. First try, 31st of August. It was late at night at that time. Where the moon. So this was the moon at that night. We when pointed the telescope at the moon, there was like a particular section of the moon was only visible in the frame at once because like telescope will obviously zoom in the image and you will only see a part of the. That depends on the magnification of the telescope mostly. So as the 18th telescope, we were only able to see like edge of the moon. This is the moon we divided in horizontal sections because we were lazy. We will get to know why. Actually, just like this material was visible at once. So, as our laziness was too much, we just adjusted the sensor and pointed the telescope toward the moon. And as the moon is moving through the sky, we just like captured one image every 25 milliseconds. So we get a video. But it was not a video, just had images. As the moon passes by, our sensor was capturing data while going through this phase. So we will get a output something like this. Where is the video? Something like this. This is the images that the telescope took during that time, stitched together in a video using a Python script. You should attend your CS classes. It helps. To get this video. That's it. It didn't work because like to get an image, you actually capture a lot of data and then stack it together. Note the word stack. We will talk about it later. So, but stacking requires a like object in the image, like a feature in the image that should be right there for long duration of time. But as the picture was moving, there was no feature that was in the image for a long time. Hence the data was like usable but hard to process. So second try, it was 4 in the morning and we were capturing data. Moon, we took moon again, obviously, and we divided it up in 12 sections. Each section was like the amount of moon that was visible in our telescope using the sensor. 12 sections. Then we focused on only one section, something like this. We took this section and captured 2000 images of this one section, which resulted in about a minute of a video, like a minute and 20 seconds. And that video file was of 9 GBs. One video file, only 1 minute. So 9 GBs, one section, 12 sections, about 100 GBs. 108. Yeah, but it was 100. And we took the date to new software. So we saw that this is a video file. We can play it in VLC. We played it in VLC, and this is what we saw. Trash. So moral of the story: don't play raw video files in VLC because VLC can comprehend the data. Now let's come back to stacking. Stacking, their definition. Secondly, we like capture a lot of data because every time you click a photo, there is a lot of errors, noises in that one single frame caused by atmospheric disturbances, you moving around, or some other thing like noise pollution and what else is there? Vibration that is caused to the so, for example, someone took 283 frames of the Jupiter. That looks like a fuzzy woolen ball, but when you take like stack 56 photos of it, stacking just means like you take one photo, put another one on top, then another one, then another one. If you do that 56 times for this particular object, you get something like this. I did that. So you have improved that image a bit from that woolen ball to this Jupiter looking. So this is the reason why we took 2000 images of the that particular section of the moon. Now moving on to the story. After tagging all the 12 sections, we got this jigsaw puzzle looking pretty, which are all the parts of the moon. After like we are in the middle of talking right now. We stacked top 5 percentile of the photos. Top 5 percentile meaning we like the software that use gives the quality. Each one of the frames is there like 2000 frames. When you can judge so like is in the photo, if there is a dust particle that randomly showed up, if there is a bird moving uh, in front of the telescope, anything. So top 5 percentile of those frames are only eligible to make it to the image. Relatable, right? You can take this jigsaw puzzle, solve it. We get moon. Actually, it's not solve it. We just put it in another processing software that stitches it together. We get this moon. It is unedited, wrong. It looks like moon now. Before it was not because it was like sectionalized and all that, like butchered in different sections. Now, after we get this photo, we can actually bring out more details using sharpening techniques and reducing noise reduction techniques, and we can increase the brightness of it. It's too dim. Then when we do that, look, it looks cool. We get the final image that we sent to Gayatri. So that's basically it. That's how we took that image. We actually used the 8-inch telescope. If we use the 11-inch telescope, the photo would be better, probably up to 8K or 10K resolution. We don't know yet. But the data size would be in terabytes. My laptop doesn't have that kind of storage. So next, that's it. इतना से समझ में आया क्या? No questions.
पूछो ना कुछ पूछो ना कुछ
Don't not like here you can see that this grainness in the image, like you can see the grains, right? Black dots, and random fuzziness. It is caused by the noise. If like your telescope is vibrating, you will get like a shaky image. When you take a photo, if your hand is shaking, you will get a shaky image. For example, atmospheric disturbances. Is there cloud is moving, brightness will dip, or like the image will shaky, you can get like jagged line like this. There is a lot of noise that affect your photos. That's why we do study to reduce them. We increase our signal to noise ratio. We need signal and we don't need noise. So after tracking, we get better looking image with less noise. Anything else? Yeah. The planet had an atmosphere, then it is difficult to take a plane water. No. Jupiter has an atmosphere. Where is it? Planet's atmosphere, like the object wouldn't affect the image that much. Our Earth's own atmosphere affects the image that much. Like anything else?
Yes. Hello everyone, I'm Gayatri from and here Shiraz. Shiraz. So first of all, why positional astronomy? We need to know the position of the stars to look. What we need to do. For example, as Vishal was talking about astrophotography, he showed you the picture of Orion Nebula, for example. How do you know where Orion Nebula is? And how do you track that across the sky using the that's positional astronomy. So yeah. So before we get to the sky, let's talk about it. How do we locate places, locations on you? Right. So when yeah, exactly. That's it. So what are those reference lines on? 2D cycle surface. On the 2D cycle surface, we have reference lines like the latitude, longitude, and some zero lines which we have defined, like equator, prime meridian, you can do the same thing with the night sky. How? So imagine you are standing somewhere looking at the night sky. You project the sky that you see onto a sphere, right? So you are at the center of a photosphere and the night sky around you, or any sky that is around you, is a sphere. That sphere is what we call the celestial sphere. So, celestial, imagine the Earth is somewhere here, and the celestial sphere is basically the sky around which, sky around it, basically. And as the Earth, the stars are pretty much stationary, but Earth rotates, so by due to the relative motion, the celestial sphere, which rotates all over the place. On the celestial sphere, again, we have some reference lines like the equator. So basically, imagine if the Earth is here, if we project Earth's equator onto the celestial, something called the celestial equator. And we have the North Celestial Pole, which is Earth's North Pole projected onto there, and South Celestial Pole. Same. Our numbers are pretty bad again. Those persons. So, yeah, coordinate system. So we need some coordinate system to learn about it. So we'll get to some there are many coordinate system. We'll get to the most used one. So yeah, the horizontal or alternate system. So if any of you have attended any of the observation sessions, you might have heard of things like the alternate mount or the equatorial mount. Yeah, so they use it. So what is the alternate system? It's the simplest coordinate system. So imagine you're standing somewhere, the horizon around you is kind of equivalent to the x-axis. The zenith, you all know what the zenith is. Yeah. The highest point in the sky is opposite to it is the number. So yeah, whatever the horizon around you is where we define the zero, and highest point is the zenith. This thing, the y-axis sort of equivalent thing, is called the altitude of any celestial object. And similarly, the azimuth is basically the x-axis equivalent. In this case, it starts from north goes from 0 to 360 degree, and the uh, altitude goes from 0 to 90. Pretty obvious, pretty simple. Now, some of you might have noticed a problem with this. Problem is that the sky that you see at a particular place and time is unique. You can't translate that to someone else, say, in some other part of the world. So you can't really communicate with that, right? You can't say, yeah, you can't basically communicate with that. So that's where we need a more universal system where the x and y axis or the equivalents are more universal. So that's where we come back to the celestial equation. Now remember the celestial equation. This is a fixed line for everybody on the earth, right? So this is a new x-axis. We need a y-axis, which we have defined pretty arbitrarily from the non-celestial pole to the zenith at your particular location, the south celestial pole. This is something we call a great circle. A great circle is just a fancy name for the largest circle you can draw on. So yeah, we have the celestial equator here, and we have the something called the celestial meridian. And you have to remember prime meridian, right? Sort of the it's the celestial equator. And from the celestial meridian, we start measuring of the hour angle. It's measured in hours instead of degrees. We'll see why it makes a difference. Actually, easier. And declination is basically, yeah, it's basically like altitude, but it starts from the celestial. So, third one, for determination and the R angle. So, R angle is basically, like I said, the angle from which any object is from the celestial meridian. It's measured like this from 0 to 24 degrees. So, example, this random object x will be at some around in this image, I think 20 or so. So this would be back to 20 hertz. So as you can see from this image, that is the zenith. When is x closest to the zenith? It's pretty clear from this image. X is closest to the zenith when x is on celestial meridian. That means x culminates. If you translate it to what you will be seeing on the night sky, will be like any object. Can everybody see this moon? So in the night sky, say this is your horizon. Any object will travel, say, and in path like this. This point, you will see. This point is basically your highest point that particular object is reaching. That thing phenomena is called culmination of that. So as you can see, when x or any object will culminate when it's on the celestial meridian. So and then for the celestial meridian, that's where we define as zero. So in a way, we can also say that when the R angle of any object is 0 hours, that's when the object will culminate. This we will get back to. You'll understand. We'll do a problem at the end. You get a better idea. So let's come to the second equatorial of everyone take the equatorial mounts are what we usually use in the 6-inch and 8-inch telescopes here. Even the 11-inch has an equatorial mount. The 11-inch also has a mount. So what is the equatorial system? So one problem with the R angle declination system was that the sun changes from place to place and time to time. So we need an even more universal coordinate system, right? So the celestial equator is pretty universal, but the zenith is not. So we define a very arbitrary an arbitrary point called the first point of Aries. It's currently in Pisces. But yeah, this is a random point we have astronomers have collectively agreed on. This is where we start the zero from. So remember the R angle. This is right assumption is basically the R angle, but it starts from this first point of Venus. This is also called the vernal equinox point because when the sun, okay, get to that later. Yeah, so majority of sun will travel on this element. So sun is not a fixed star. The stars are all pretty much stationary objects in the night sky. So they are all basically fixed on celestial scale. But the sun is not fixed, it's pretty close to Earth and it will not follow a very fixed path. So, what the sun actually does, it follows a tilted path. As you can see, this line, blue line is what the sun will travel. Why is it so? Well, you all know the Earth is tilted by 23.5 degrees. So, because of that, the sun's path is also called the system rather, that is tilted from the celestial equator by this 23.5 degrees. So that is the sun's path, and the reason we call this point, the first point of Venus, like I said, called the equinox point, is that when the sun, this is the sun's path throughout the year. So when the sun is at the vernal equinox point during a year, that's when we'll have like this, the vernal equinox, which is on March 23 or 24. Yeah. Yeah, and the common source is when the sun is at the highest quantum. That means it will spend the most amount of time in the in the sky basically, which means the longest day. That's the summer solstice. And similarly, winter solstice are not the longest one. Yeah. So another thing, diurnal motion of stars. Diurnal means throughout the day. So throughout the day, how does it start? Move across the so actually if we compare to the previous diagrams, as you can see, the horizon is tilted from the celestial equator, right? Because of the latitude. If you're at the equator, this should be pretty much the same value. But if you're not, it will be tilted by some, and that and depends on latitude. So if you tilt this entire diagram such that your horizon is horizontal, that's how you basically see the night sky looking from here, and this is the horizon. You can see that all the stars, like I mentioned, all the stars have this weird shape, like this kind of parabol. This shape, as you can see, because of the Earth's core. So as you can see, all the stars will travel along this red line or yeah, basically any line along the yeah. These points are how this you see some stars which are higher up with higher definition don't even go below the horizon. Basically, you can that translates to the fact that the stars never set in the sky. I mean, in the night. They basically stay in the sky. Can see the not the day theoretically you can see. And those stars are called circumpolar. Yeah, it's just terminology. It's most of the next we'll come to a very interesting concept called the sidereal time. So, what do you think of when you think of what is a day? Day is basically as you know the time it takes for the to rotate, yeah, complete rotation. But what are we defining the day of? So when we actually say day, what we actually refer to is a solar day. So basically, it's the sun is at one particular point in the sky, and we'll start a clock. And in exactly exactly 24 hours, sun will be same point in the sky. That is what we call solar. Well, actually, the Earth is also traveling along one orbit around the sun. Because of that, the solar day is actually not same to sidereal day. So, what exactly is a sidereal day? Sidereal day is just a fancy term for a day, but instead of the sun, the reference frame is the background stars. So the background stars are pretty much fixed; they are stationary. On if we instead of the sun, if we start the clock, then like I said, okay. So imagine the sun and the background star at one location. We start the clock in exactly 23 hours 56 minutes. Uh, the star will reach the same point of the star. But the sun will not. The sun will take an additional 4 minutes, approximately 4 minutes to reach the same point of the sun. Okay, can anybody survive with 4 minutes as well? Isn't that exactly. So, as you can see, the orbit is roughly circular, and if you take in one day, one day, as you might remember from basic geography classes, takes like 4 minutes to travel 1 degree. So this 1 degree, this extra 1 degree that the sun the Earth has to rotate, so that the sun will reach the same position back is 4 minutes. That's what we call solar day, and a sidereal day is actually shorter than a solar day by 4. What this translates to is that throughout an entire year, basically my days, this 4 minute gap will actually add up to 24 hours. So it's actually important for astronomical observation. We don't define the system based on the sun, right? Based on the background fixed stuff. So again, some more facts about this very fun. So basically, we need a reference point. We need a creator. So what astronomers have come up with basically is that uh, at the vernal equinox, sidereal day and solar day will match up perfectly, and throughout the year they will increase and keep on increase and keep on increasing, and by the time next vernal equinox, it will add up to an extra 24 hours, or an extra day. That also means that during the autumnal equinox, the sidereal time, the local sidereal time is 12 hours. We'll come back to that later. We'll come back to that later. Um, Again, sidereal time is basically the hour angle of the world. Now, this sounds like an absolutely garbage line, but it's actually pretty easy to understand. So, if you go back to hour angle thing, basically, when the vernal equinox, when the vernal equinox is at the celestial meridian, that's where we define a zero from. That's when the vernal equinox happens. So that's where we define a zero from. That's why it's called the R angle of the vernal equinox. R angle is basically a time it takes for like from the last termination. R angle is the amount of time since the last termination. So if you remember, the culmination is the highest point in the sky. R angle is zero at the culmination. So if R angle is say like let's say 1 hour, which means it has been 1 hour since the last culmination. So this is a bit more maths. It's easy to understand, but it's not very obvious when you follow. So basically, sidereal time and right assumption are how are they related? So the local, what I'm claiming here is that the local R angle of the star is the local sidereal time minus the right assumption. How exactly? So the local sidereal time is Okay, so if March 21st is when we start the vernal equinox. On March, on the next day, before midnight, 4 minutes before midnight, the sidereal day actually ends. So at midnight, this local sidereal time will actually be 4 minutes, right? It will be 0004. While the solar time is actually 0004. The next day that will add up to 8 minutes, so on and so forth. So that's basically what the local sidereal time is. So if you and throughout the year that will add up to 24 hours. So at the autumnal equinox that will be 12 hours. So the local hour angle of the star is the local sidereal time minus the right ascension. Or another way to look at it is that suppose the local sidereal time is 1 hour. It means the vernal equinox has moved 1 hour west of the meridian. So this is the celestial meridian, and the vernal equinox point has moved 1 hour. So it moves somewhere over here, right? So imagine X is somewhere over. Sorry, the vernal equinox point is somewhere over. So that means somebody will be at the celestial meridian. Come on, let's say X. So now the vernal equinox and the distance or the angular distance between the vernal equinox and this x, which is here, it's not that exactly because that's how we defined it. But the right ascension, if you remember, was also the angular distance from this vernal equinox. So basically, what we see here is that the right ascension is equal to the right ascension is equal to the angular distance from the vernal equinox. So for any star which is on the celestial meridian, which means that our angle is 0, the local sidereal time is equal to the right ascension of that star. If you don't understand any of this, just memorize this. Maybe separate days to understand this. So yeah, in order to so let's do a very small problem to apply these facts that we learned. We'll get you much clearer with the concept. So, okay, let's say the time is 7th October 2023, 7 minutes. Doesn't matter. How do you find the local sidereal time? Right here, or at 7 p.m. So, as you know, on 23rd September, we had the autumnal equinox. And as I mentioned earlier, the autumnal equinox, the autumnal equinox, sidereal time is 12 hours at noon. Why? Because it's been exactly 6 months since the vernal equinox, and that's where we started the year. So let's add 12. Let's keep that 12. So, okay, so today at noon, it's been 14 days since the autumn. How do we translate that 14 days in? So 14 days is 14 by 30 months, and every month the local sidereal time advances by exactly 2 hours. Why? Because it advances by 24 hours in a year. So it advances by 2 hours. So basically multiply these things, we'll get decimal number which are converted into digits minutes. Okay, so that's the local sidereal. Okay, so 12 hours plus 56 minutes is the local sidereal time at today noon. During today noon, this is the local sidereal time. 12 hours plus 50. Now it's 7 p.m. now, it's now 20 minutes. At 7 p.m. it's been 7 hours since the noon. So if calculability, you just add things up and you just add these things up and you get 19 rupees. That's the local sidereal time at 7 p.m. Now, how do we use this? Why did we calculate the local sidereal? Okay, now let's actually do something more practical. Let's say you want to image Sirius. I don't know why you would image Sirius, but pretty boring star. Even then, let's say you want to image Sirius and you can image any object in like at the highest score. It's the path furthest from your horizon. Like, so let's find the culmination of series. So we want to make series and we want to find when it's at the highest point in the next sky in your local sky. So let's find the culmination of series. So the right extension of series is 6 hours and 45 minutes. Just Google that. The right extension and explanation for most basically every star or any fixed point in the night sky is almost fixed. The small minor precision due to precision and wobbling nature of Earth's orbit, but yeah, it's mostly fixed for our purposes. It's a constant. You know the right assumption of series. R angle, we saw the formula earlier, the satellite dimensional motion. Subtract that, you'll get 3 hours and 11 minutes. What is the hour angle again? It's the time since the last 5 minutes. Another way to look at it is that we can also say that in 24 hours minus this number, series will culminate again. So what we can do is we'll subtract it from 24 hours. We'll get 10 hours and 49 from now. From time here. That's when series will culminate. If you add that up, you'll get something like morning 5:40 is when series will culminate. So you now know when you can image series the best, right? So yeah, that's how we can translate something very abstract like local satellite time acquisition, blah blah blah, to something actually useful and practical. You can use in your astronomical observations, astrophotography, whatever. Now, is this time accurate? Approximately. There are some problems. There are one significant problem I don't know if you've noticed, it's not very obvious, is that we've taken the time to be 7 p.m. It's not exactly 7 p.m. 7 p.m. is the time in at 28 at 82.5 degrees longitude, right? That's the Indian standard time. Jatni, it's like it's around 3 degrees before that, so there's a bit of the actual time is not really 7 p.m. So there's a bit of yeah, that's where it can go wrong. But for our case, it's almost right. I actually checked it on Stellarium. You guys use Stellarium. You can actually check the culmination of series, and it's 5:40 a.m. Yeah, prove that I said that altitude is the maximum, and tomorrow 5:40. So that's maximum. And spherical astronomy is actually much more complicated than the other scheme. So much, actually, so much trigonometry and with that, honestly scared of and put it in the slide. This stands for yeah, these are the basics of it, and you'll get to know more as you attend more and more of that. Observations and things. Please do attend them. You can see the norms and stuff. You'll better understand the tutorial and algorithm system that we mentioned. So yeah, that's
all of that. Because we will be asking questions from 100% goes for it. Switch. अभी कुछ और बना रहा है सेक्शन को डिस्कस करना है वो कुछ कुछ तो करें चार्ज चार्ज हो जाएगा
You know, this way.
The works on for no. Chico. Kaya ko ganito. Mga to kali din eh chicken gan. Ja. Chubro. Stop.